Okay, I'm Ron Fant.
Hi, Ron.
I don't know.
The P3 was last in Salina in 2015 for the Plains Elevated Convection at Night experiment.
I did Hurricane Lane was my first hurricane penetration, and then Florence and Michael. So right now I've got 3 Cat 5s under my belt.
My name is Conrad Ziegler. I'm a senior research meteorologist at the NOAA National Severe Storms Laboratory in Norman, Oklahoma, and I am the chief research scientist with responsibility for the science missions that are conducted by the NOAA P3 aircraft during TORUS. And I'm a co-investigator on the NSF proposal for TORUS. So we studied nocturnal mesoscale convective systems during the Pecan experiment in 2015. So that was a much different mission profile than TORUS, which is looking at daytime supercells this season. So in Pecan, we looked at nocturnal convective systems, so often the takeoff would be early evening, late afternoon or early evening, and then we would fly actually over a similar range as TORUS, but we were flying mostly after dark in that experiment, whereas in this experiment we're doing most of our flying during the daylight hours with a little bit of flying after dark. So in this experiment, as you heard from the speakers this morning, we're very puzzled as a community about why only a few supercells produce tornadoes. We basically learned from the first vortex experiment during the early and mid 1990s that supercells are responsible for the majority of especially violent tornadoes, strong and violent tornadoes. But one of the other things that really puzzled us about the lessons from the first vortex were why only a relatively small fraction of supercells produce tornadoes. So I would say one of the key questions for TORUS is what are the specific internal characteristics of thunderstorms, especially characteristics in low levels and near the surface, that cause one supercell to either produce a tornado or not produce a tornado. We're basically interested in those decision factors that the storm uses to figure out whether it will produce a tornado or not. And as we know a priori, supercells can be prolific, violent tornado producers. They don't usually produce tornadoes. So there are a lot of supercells that don't tornado. There are a lot of supercells that for the majority of their life cycle don't produce tornadoes. So we would like to try to unravel those questions in TORUS. So one of the key differences about TORUS that is different than previous projects is that we have developed and brought to the field a capability to fly unpiloted or remotely piloted aircraft that have weather instruments, so they can get in very close to the storms and begin to measure details such as converging air currents between warm, moist inflow and cold thunderstorm outflow. We have developed hypotheses that suggest that in a number of supercells, details of where these boundaries are placed with respect to the location of the main updraft, or even whether these boundaries exist in a given storm or not, may be determining whether some supercells produce a tornado or not. So a key is to measure these low-level features such as boundaries between air masses produced by the storm that may be in turn making it more or less likely of a tornado being produced. That we look at the storm scale features, the larger features, the updrafts, downdrafts, low-level mesocyclone, mid-level mesocyclone, any outflows, and we believe outflows may be important for whether a supercell produces a tornado or does not. So we can map those features that I like to refer to as storm scale. So when you look at a storm on radar, you're seeing the whole storm. We're seeing features within that storm scale. Then the ground teams are looking at finer details. As you saw with the vehicles inside the hangar, we have a lot of ground-based vehicles, many participants on the ground in the field, and that is the core of the experiment. But we have the NOAA P3 aircraft, which will be contributing its observations. I am the chief scientist on the NOAA P3, so my role is to work with the NOAA flight crew, and what I will do is I will request that the aircraft fly to a given targeted storm that the ground teams will be working on, and I will request that the AOC set up flight legs back and forth in the inflow with our radars pointing at that target storm, and we will simply collect data from the entire storm over the life cycle of the storm. So we're flying back and forth, seeing a view of the three-dimensional air currents in the storm and how those evolve over time, while the ground teams are collecting more detailed measurements.
My name is Edward Mansell. Well, I'm at the National Severe Storms Laboratory in Norman, Oklahoma. It's part of NOAA, National Oceanic and Atmospheric Administration. NSSL is kind of the research side of that does basic research that helps create new forecast strategies and products that can then transition to the Weather Service to improve their forecasts, and all in the mission of saving lives and property. I'm originally from Pennsylvania, and growing up we had a tornado that hit my hometown, so that was part of an interest in weather. Yeah, well, I ended up in weather kind of along the way. I was in a physics track, and so actually my degrees are in physics, and then in my doctoral work I worked in thunderstorm electrification, studying lightning and how storms charge up and make lightning. I'm not one of the principal investigators, but I am, and colleagues are operating this radar in support of the project, and our main purpose is to provide storm scale surveillance of the storm to help characterize the structure of the storm using the Doppler radar, and also frequent low-level scans to look at features that could be important in the production of tornadoes. There have been competing ideas whether the tornadic winds start to form aloft or down at the ground, and that provides a very good example. The initial spin-up happens at the ground and grows upward through vertical motion that stretches that vorticity and strengthens it, and then you see grow aloft, sometimes very quickly in this case. And most ideas now are saying that the initial rotation for a tornado comes from back behind in the outflow, where that vorticity is actually at the ground and just needs to be strengthened. And it's that process of getting it strengthened and having a successful spin-up that starts the tornado. And after that, once it gets going, then it can wrap in these tilted vortex lines and wrap it in higher up. But to actually get it started at the ground, it needs to have something special. So I work on the parts of the physics that describes how raindrops freeze and make hail, and all those liquid ice processes in the storms that are important to storm properties. I mean, roughly we're talking in terms of the equipment and the hours spent of the engineers, easily $1 million total for everything. Yeah, aircraft are another order of magnitude. Well, they won't be flying through any storms on this project. They just do that for hurricanes and on the backside of squall lines. They'll fly through stratiform regions, but they don't like to fly through strong updrafts or anything that might have hail.
Yes, the NOAA Aircraft Operations Center, or AOC, as I refer to it in short, is the NOAA organization that operates the NOAA P-3. So they maintain the airframe, they maintain all of the instrumentation that are inside the aircraft. This is why we have the aircraft here. It's a scientific data gathering platform as we apply it, and they are staffing all the flight crews. There are ground crews that maintain the aircraft out here in the field. So there's really a large NOAA contribution, both in the air and on the ground, to keep the aircraft operating and keep in peak condition.
No, we're operating out of Salina, Kansas for the next 6 weeks. We're doing this TORUS project. Yeah, we're going to be flying on supercells all around. So.
Oh man!
It's looking like Thursday, Friday, it's going to start lighting off. So yeah, pay attention to the TV, and you might see us or hear. Lieutenant Brian Richards. I'm a navigator. This is my station right here. This is where I live and breathe. I was prior military. We are NOAA Corps, so the NOAA Corps is one of the 7 uniformed services. So I'm technically still active duty. So all the pilots and navigators that fly these planes are active duty NOAA Corps officers. Yeah, but it's just different. You know, coming over here, you're it's more scientific. You know, you're working around these weather cells that you know, when I was back in the Navy, you used to totally avoid. So it's definitely a different way of thinking. Yep. So I've been here since 2017. So I made it through 1 hurricane season, and before that, I did 2 different projects. One, we were flying out of Ireland, and that was for satellite data validation with NESDIS, and so that was really cool, flying on North Atlantic storms that, you know, were kind of cyclonic in nature, and essentially you're looking for high wind fields. You want to be right there, you know, flying over at the same time as the satellite. So that was really neat. That was really cool to see. And then I did the basis of this project. I did basically the same thing, flying out of Huntsville, Alabama, last year. So doing supercell research. I can count 3. I did Hurricane Lane was my first hurricane penetration, and then Florence and Michael. So right now I've got 3 Cat 5s under my belt. Yeah, so it kind of depends on the mission. You know, we've got our onboard navigation system, so 2 GPS embedded inertial navigation units that, you know, if they were to lose GPS signal, they could still run, you know where we are. And then I also, you know, communicate. We've got 2 HF radios, long-range radios, so if we're ever operating, you know, out in the middle of the ocean, I'm the guy that's talking on the HF radios with ATC or anyone that we need to communicate with, and we need to use those high-frequency radios to do so. So if we're talking hurricane specific, I kind of look at where the hurricane is, where the hurricane's going to be, and then I work with the flight director and the pilot to kind of position the aircraft to where it needs to be, because we want really nice straight level legs. For this mission, for TORUS, I'm kind of more so on the safety side, so I'm looking at all the surrounding terrain, because we want to maintain 2,500 feet AGL. We'd like to keep it straight level. We'd like to stay at a set altitude sometimes. So I'm looking around, looking at all the different towers and, you know, safety altitudes and stuff like that. So I'm constantly communicating with the flight director and with the flight station about what altitudes we need to be at for this specific mission. So. Yeah, I don't necessarily know if we want to fly through those updrafts. We try to stay away from them when we're off these supercells. Our safe distance is going to be about 10 kilometers, which is about 5.5 miles. So we're going to try to stay there, and we're going to try to stay in as safe a position as we possibly can. If this aircraft, you know, ever gets put into a compromise or a safety compromise, we're going to, you know, use the procedures that we have to put the aircraft into a safe position. So that's key. That is the most vital thing that we're doing here. We want to collect this data, but we have to do it safely. Nope, no parachutes on board. We did have them in the Navy, but none on this aircraft. Yep, absolutely. Yep, keep the wings level.
I have to keep track of where are the ground teams, what storm are they working, how is the storm evolving, where is it moving, are there other storms that are coming up nearby that might encroach eventually upon our flight legs, and then to figure out a set of flight legs that have the best chance of giving me the kind of data that I want from our radars that we carry on the aircraft and the other supporting observations that we obtain. Then after I make a request, the AOC decides whether they can safely meet my request. They always try to meet the request, but if they have safety concerns that are triggered, then they will say, well, we'll have to try another sampling strategy than the one you requested. We have our 2 radars on the P3 that are scanning vertically. We have Doppler velocities from the lower fuselage radar, but it's only really looking at one tilt in the low levels of the storm. We also have the NOXP, NSSL, mobile ground-based radar, and that will be scanning the storm from the ground, so that by combining the look angles from each of those radars, we can get a complete picture of the three-dimensional internal air circulations within our storm.
Akshay Patel. So I'm going to be I'm on training with the radar people, with the chief science crew here. So usually I do drop zones when we are in hurricanes, so that's my role. But for TORUS, we're going to do not dropping any zones, so got to do radars. I've been working with NOAA for 2 years now, and I'm a structural engineer. So anything goes on the plane, any mounts, any instruments, we do structural engineering for it and get approval and mount it. I'll be sitting right next to the station 3, where I'll be looking at radars. Yeah, this is like we usually have like 8.5 hour flight, so we don't want to fatigue any crew members, so they have a bunk bed kind of thing, a coffee, microwave, you can come eat here. Yeah, this is like, I'm telling you, this is almost 8 to 10 hours job once you start. From a pre-flight till we land back, it's almost 10 hours job. So when we're in plane, it's almost 8 hours to 9 hours. Sometimes we stretch, depending on missions and how it goes. We usually get 9,200 gallons of fuel in it, so which is a lot. We can run a Prius for 70 years.
We have funding for 2 field phases, and the research will be commencing essentially immediately as soon as we start collecting data this year. Then we'll complete this year's field phase. We'll have another field phase next year. Our thinking on that, and that was a key part of the planning of the experiment, is that we want 2 field seasons in order to collect enough data on strong enough storms and a broad enough sample of strong storms so that we can test our science hypotheses.
We will not be playing a part in this, but we would like to get access to some of their data and some of their pictures that they see in their video out in the field while they're out there, because that will help us do our job a lot better, but we don't actually have a role in
they
this
may be
project.
reading our discussions, forecast discussions, stuff like that to decide where they're going to deploy. And that's possible. They could be looking at our forecast, our discussions, just to kind of help them out as far as where to go for severe storms, especially if they're in Kansas.
It's, in my opinion, thunderstorms and especially supercells are very complex, but there is something going on the ground that's unique that makes that whole process come together to generate the tornado. That's why not all supercells produce tornadoes. Some of them do, some of them don't. And because it's such a complex system, there's some kind of mystery going on down low that we just don't quite understand yet. Well, this is a big step in the right direction to try and help uncover some of those mysteries, is during research projects like this. I think at some point, I can't put a date or a timeline on it, but we will start to see things a little bit differently and be able to maybe improve our warnings and try and get ahead of this a little bit quicker than we can right now. There's a very strong upper level jet for this time of the year. which makes the situation really volatile. If things come together just right, what the long-range models are showing, we could have a pretty big tornado day, and some of those tornadoes could be long-track tornadoes. And that could lead to an outbreak if things continue to stay together like the long-range models are suggesting. I think they're going to have a lot of interesting storms and setups to look at here.
All in the mission of saving lives and property.